Hello, welcome to section 1.6. We are going to be talking about displacement and velocity. These should all really be kind of review. We might be going a little further with some of these ideas than you have in the past, but I need to make sure everybody at least understands the basic definitions. So let's do a little bit of review, and we're going to look at displacement. We're going to look at what distance is, average velocity and versus speed. We're going to look at different applications in graphing and what displacement and velocity look like on graphs. We're going to look at also instantaneous velocity and how we can calculate something like that. So let's get started. First, we are going to begin with simple one-dimensional motion. When I talk about one-dimensional motion, I'm not talking about something going in only one direction. I'm talking about something very much like a railroad track. This train could go forward or backward on that track, but that track limits us to one-dimensional motion. It can go plus or minus on there. Frame of reference is another important concept in one-dimensional motion. We have our train and the motion of the train on this track. We have a lot of other motions going on. We have the motion of the earth. We have the earth spinning around the sun. Who knows, whatever. People that are walking about on the train. But if we're concerned with only this one-dimensional motion of the train on this track, we need a frame of reference to help us. The station, for example, might be something we would choose as a frame of reference. Maybe the station and station A and station B. We could say that if the train is going from station A to station B, it is going in a positive direction. If it is moving in the other direction, that would be the negative direction. That gives us a frame of reference so that we know we can describe the motion. In physics, we can choose any frame of reference that we want to describe a system. However, some frames of reference are obviously going to be more convenient to help us describe the motion than others. With that being said, let's look at this idea of displacement. So when we talk in physics about displacement, we are talking about a change in position. So as that train goes from station A to station B, its displacement would be the final position, station B, minus the initial position, whatever the measurement would be at station A. Another way that we write displacement would be delta x, or change in x. We can say change in x equals xf, this f stands for final, minus the position I, or the initial position. F stands for final, I stands for initial. One important thing to note is that displacement and distance traveled is not the same necessarily. They might be equal, but they're not the same thing. When we talk about displacement, it is the final position minus the initial position only. That is the displacement. Perhaps this is a little butterfly traveling. The displacement of this butterfly is this location minus this location. But the distance it traveled was something quite different. Look where it went, all around. That was its path taken. That is what distance is. So displacement and distance are not equal. Here is just a quick little example. Let's say we have our car starting right here. We'll say the front of the car starts right there at 0 kilometers. And we're going to make this scale right here our frame of reference for us. And that's what we will use to determine the displacement of this car. Let's say this car travels and then stops right there. What would be the displacement? The displacement equals delta x, which equals xf, the final location, minus the initial location. Our final location, xf, is 20 kilometers. Our initial location is 0 kilometers. So this should be pretty easy to do. We can say in this case that the change in displacement is equal to 20 kilometers minus 0 kilometers, which is just 20 kilometers. Now this seems really simple and ridiculous for me to go through this, but I just want to make sure that everyone understands and that you can do problems like this when they get more complex. What if our little car went, what if it started way back here at a negative 10 kilometers? And when it traveled, let's do a different color here. It's traveling from negative 10 kilometers to 30 kilometers. Well, how does that work? We know that our initial position is going to be negative 10. Our final position is going to be 30 kilometers. So in this case, our displacement is simply going to be the final, which is 30 kilometers, minus the initial, which is negative 10 kilometers. So a double negative here, a minus a negative is just a positive. It's going to give us 40 kilometers. So you want to definitely keep track of your negative signs, and this is really useful because we're using this as our frame of reference and we're being consistent. It really doesn't matter where we stop, where we start, as long as we're consistent with our frame of reference, we will be able to determine the total displacement. So displacement could also be negative, right? We could have our car starting right here at 30 kilometers, and let's say it ends up right there. In this case, our initial position is 30, and our final position is 10. So the change in position, or displacement, is going to be 10 kilometers for the final, minus 30 kilometers for initial. So in this case, we will be negative 20 kilometers. And that's very important. That tells us the direction that we're going. That brings us to another concept that I'm sure you're familiar with, average velocity. What is velocity? So it's nice to know that the train traveled, went from point A to point B, but it might be nice to know how fast it was going. And in order to know how fast it was going, we need to relate its change in position to its time. We need to know how much time it took for it to change that amount of position. And we know that the average velocity is equal to the change in position divided by the change in time. Here I wrote it out in words. Here I wrote it out in symbols. The change in position, remember, is the displacement. The change in time is just the amount of time that elapsed while it changed in position that much. So when we write average velocity, it's a V, an AVE in subscript indicates average. Remember the delta, change in position over change in time. Another way of writing that when we write change in is the position final minus the position initial, or the time final minus the time initial. Velocity is not, however, equal to speed. Those are often used interchangeably, but you probably already know speed and velocity are not the same thing. The average speed is just the distance divided by the time. Velocity, however, describes the motion with both direction and a numerical value. So speed just has to do with a numerical value. Velocity has to do with the numerical value and the direction. This little guy is just reminding you velocity is basically speed with a direction to it. Here is a sample problem. Let's say 3 students are walking due east with an average velocity of 0.95 meters per second. What distance have they covered after 30 minutes? And that period is there to indicate that there are 2 sig figs in that number. So what do we start with? What do we know? Well, we know their average velocity is 0.95 meters per second. We also know the change in time is 30 minutes. Velocity and graphs. So here's a quick little review. If you don't remember this from previous science classes, this is a graph where position is plotted versus time, a position versus time graph. Position versus time, here when we have a constant velocity, it will look like this, and the slope of that line will be an average velocity. And the reason is we know that slope, remember from math, is rise over run. Rise is going to be the change in position. Run is going to be the change in time. So when we have the change in position over the change in time, remember that is average velocity. It's change in position over change in time. That's the rest of the formula there. So when we measure the slope will be our average velocity. So let's take a look at some more position versus time graphs. And these will not be quantitative, but just qualitative graphs. We had said before, if we have a graph that looks like this, we have constant velocity. So when we have, if we plot our position versus time and we get a line like this, it is constant velocity. If, however, we get a line that looks like this, straight across, that means our object is in rest. It means that for all this time that's going by, it is not changing position. Okay, now if we have a graph that looks like this, our object is moving with constant velocity. What's different about it? It is constant negative velocity. This one shows constant positive velocity. As I go along in time, it is increasing with positive position, going somewhere positive. This one, the position is going somewhere negative, so that would be a constant negative velocity in a different direction. Now that brings us to another idea, and that is instantaneous velocity. Instantaneous velocity is not the same as average velocity. Let's say we have a position time graph or displacement time graph, and it looks like this green line right here. This green line is representing the movement of our object. That is not constant velocity, is it? It is definitely changing velocity over time. If we have something whose velocity, an object which velocity is changing over time like this, how are we going to find its average velocity? How are we going to find maybe the velocity at any given point on here? Those would be different, wouldn't they? If we just pick a point, let's say this point right here, and we say that at that point I would like to know what the velocity is of this object, that would be called its instantaneous velocity. And the way we can find that on a graph like this is take a tangent to that point on the line. That tangent right there will end up equaling the instantaneous velocity. And we know that because we can, again, here is the change in position, the change in displacement, which is the rise over the change in time, right there for that tangent. That gives us the velocity, and it gives us the instantaneous velocity for that point. That is not the overall average velocity, however. It may or may not be, but you cannot assume that those are equal. So here's just an example of how I would calculate that. Let's suppose that we have graphed the movement of an object here, and we would like to know its instantaneous velocity at some point, at that point right there, at 4 seconds, and there's the point marking it. How would I go about that? Well, a tangent line has been drawn right here to that point, and I would simply plug in the values. We have our 20 minus 2.5, and that is taking 20 minus 2.5, the final minus the initial distance or position. I'm going to divide that by the run. That would be here. So that would be from 3 seconds up to about 5.6 seconds. So I take the final, which is 5.6, minus the initial, which is 3. And when I do that, I get 6.7 meters per second. I didn't include my units here, which I should have. Here, these are in meters. These are in seconds. And that gives me meters per second. That is the velocity, the instantaneous velocity at that point. And here's one last thought before we finish this section. If you ever go to a car race and you watch these cars racing around the track, around and around and around, on their car, on each of those vehicles is a speedometer. And that's what the speedometer is measuring. It's measuring speed. The speedometer does not measure velocity, because if each of these little vehicles here had a velocitometer on it instead of a speedometer, every time they got back around, they would have a 0 velocity, because they would not have displaced themselves anywhere. They would have been right back at the beginning where they started, and their velocity therefore would be 0. So it's important to just keep that idea in mind. Velocity contains not only it contains a direction as well as speed. It's like speed with a direction. That's just a really important concept to keep in mind, because we'll be working with those concepts later. Speed is only concerned with the distance traveled versus time, but it doesn't have anything to do with the overall direction. Velocity, it does. So if you are interested in some advanced ideas, try the conceptual challenge problems on page 45 in your textbook. See if you can do some of those, and I look forward to seeing you in class.